Okay, welcome back to my channel everyone. My name is Ansar, your helping hand. And in today's video, we're going to be going through another IFoA question. Specifically, this question has to do with the central limit theorem and exponential distributions. So this one doesn't really, I have a very similar video where we also go through CLT and exponential distributions, but in that video it was more about actually calculating the probabilities. This one, it's more just it's less about probabilities and more just about the theory behind the actual distributions. So as usual, I'm going to show you the question. You can read through it, attempt it in your own time, and then come back for the answers. So yeah, let's get going. Specifically, just a quick recap with the information of the question. This question comes from the 2014 paper, and this comes from the 2017 paper, specifically the April paper, and it is question 5. Okay, so let's read the question. So the question says, let x1 through to xn be a sequence of independent, identically distributed random variables with finite mean and finite non-zero variance sigma squared. The first question is, state the central limit theorem in terms of the sum from I equals 1 to n of xi. And then the second part of the question says, assume now that each xi, where I is equal to 1 to 50, follows an exponential distribution with parameter lambda equals 2, and let y be the sum from 1 to 50. The second question says, determine the approximate distribution of y together with its parameters using the CLT. The third question says, state the exact distribution of y together with its parameters. And the last question is, comment on the shape of the distribution of y based on your answers to part 2 and 3. Okay, so I'm going to let you pause the video and attempt it on your own time, and then you're going to come back and we'll go through the answers together. Okay, so I'm assuming you've attempted the question. So 5i, right, says state the central limit theorem in terms of the sum 1 to n, and this basically is not a difficult thing. I have an entire video on the central limit theorems and how we get this sum value and how we get what its distribution is. But basically, the central limit theorem says that let x1, x2, all the way through to xn be independent, so IID, and independent and identically distributed random variables with finite mean mu and finite. It's important that it's non-zero, but usually we don't really include the non-zero part because we assume that it is non-zero. Finite non-zero variance sigma squared. Then the central limit theorem says that the sum from I is equal to 1 to n of xi is approximately, right, and this approximation gets better as n goes to infinity, but when we take a particular value of n, that it will approximately look like a normal distribution where our mu is equal to the number of samples we took times by our mean, and our variance is the number of samples we took times by the variance of the individual random variables. So that's just the central limit theorem in terms of the sum and without any other information about our xi's. Okay, so the second part of our question says, assume now that each xi from 1 to 50, so our n goes to 50, right, follows an exponential distribution with parameter lambda equals 2, and let y be the sum from 1 to 50 of our xi's. So it's kind of important just to have the notation that you need. So you have x1 through to x2 through all the way to xn is independent and identically distributed exponential random variables. Now this is important. They are giving a parameter lambda equals 2. We've been taught, our theory kind of goes, or there's two versions of the exponential distribution depending on what parameter you specify. And we've learned the parameter beta with our exponential distribution, and all this is equal to is 1 over lambda. So you can either give a lambda or you can give a beta, and you can figure out the other based on this relationship over here. So because we know what our lambda is, they tell us that our lambda is 2. We know that these exponentially distributed random variables have a beta parameter equal to 1/2. Okay, so that's the kind of baseline information that we need. And then because we're going to use the central limit theorem to give the approximate distribution, we need the expectation of any one of our xi's, which is just going to be the beta random variable. For an exponential, this is review of exponential distributions. And then the variance of xi's is just going to be beta squared, so that's going to be 1/4. So then we know that y, being the sum from I equals 1 to 50 of our xi's, that's going to have a normal approximation, or normal, that's going to approximately have a normal distribution, where our mean is going to be n, which is 50, times our mean for our individual random variables, which is 1/2, and our variance is going to be n times the variance of our individual random variables. So therefore we have that y is approximately a normal with a mean of 25 and a variance of 12.5. Okay, so that's question 2, or II. This was question I. Now they want to state the exact distribution of y together with its parameters. So they do say state, they don't say prove, so you can use information you already know, or you can prove it yourself if you don't know what it is using MGFs. But I do have a video where I go through this question where we do actually prove it. But essentially, the distribution of y is going to be a gamma distribution. And this happens whenever you take the sum of exponentials, that your sum is going to have a gamma distribution where your alpha parameter is the number of exponentials you summed up. So we took 50 exponentials, and the beta value will be the same as the beta value for the exponential. So our beta value was 1/2. So this is 50 and 1/2. Okay, so that's question 3, where we just state the exact distribution. Question 4 says, comment on the shape of the distribution of y based on your answers to part 2 and part 3. Okay, so we need to talk about the shape of y when we're talking about a gamma distribution, and the shape of y when we're talking about a normal distribution. Now, obviously, this does require you to understand what the shapes of a normal and what the shape of a gamma looks like. But essentially, the shape of a normal is always something that's symmetric, right? Symmetric about the mean. That's always the case. And your gamma distribution, right? Remember, the gamma distribution can look like a variety of different things depending on what your alpha and your beta looks like, whereas your normal will always look like this bell curve. It just might be shifted or squeezed in or squeezed out a little bit, but it always has this bell curve shape, whereas the gamma distribution, depending on what alpha and beta is equal to, has very different shapes. But what's important about the gamma distribution, or one of the important parts about the gamma distribution, is that it's usually asymmetric, or that it's skew. So we have something that looks like this, where it's not this nice symmetric curve, but what the answers to 3 and the answers to 2 are implying is that as our n value gets large, so what we would say is that our approximation, right, which is the normal distribution, our approximation is symmetric, right? I don't know if I spelled symmetric correctly, probably very wrong, right? Our approximation is symmetric, whereas our exact distribution is asymmetric, right? And once again, this is probably going to be spelled incorrectly, whatever, you understand what I'm saying. So our approximation is symmetric, but our exact distribution is asymmetric. But remember that the central limit theorem says that when we take a sum of independent random variables and our n goes to infinity, that will be a normal, right? So if we take an infinite sum, then we will have a normal distribution. Sorry. So what this is saying is that as our n gets large, right, remember our n value and our alpha value are equivalent in this case because n is the number of exponentials we're taking, and when we sum up exponentials, you're going to get a gamma where your alpha value is equal to the number of sums that you took, which is the n value essentially, right? So as n gets large, right, that implies that alpha, right, alpha will get large, and therefore, right, our approximation will look normal, right? But our approximation gets better and better and better and better as we add up more n's. So that means that as our approximation gets larger, right, our n value will get large, which means our alpha value will get large in the exact distribution. So therefore we know that what this means is that a gamma distribution will look symmetric. It's probably spelling that wrong again, but our gamma distribution will look symmetric if alpha is large enough. So that's basically the comment that you have to make on the shape. It's just understanding that your approximation is a normal distribution, which is symmetric distribution, but your exact distribution is a gamma distribution, and that usually is asymmetric, right? Once you get large enough alphas, then your gamma will actually look normal, and that's what this question is implying, and that's the kind of point of this last comment that you have to make. Okay, so that's the end of this video. Please don't forget to like and subscribe, comment if you have any questions, and then yeah, I'll see you in the next video. Bye!